Dear students, tomorrow in FEM class, we're going to work with three-dimensional surface bodies. Okay, last week we have studied two-dimensional surface body, right, for plane stress and plane strain analysis. But three-dimensional surface bodies we can use, and in which case we are going to use three-dimensional surface bodies, I will explain more clearly tomorrow. So we make this shape, wait. So we analyze this shape, okay? So analysis of Bellow joints for tomorrow class using ANSYS, okay? Before analyzing, we have to create a model, okay? Surface model, 3D surface model, okay? Not two-dimensional surface model, 3D surface model, just surface model, okay? So what is this one? What is Bellow joints? Bellow joints are used to connect two pipes like this one, okay? So two pipes. So fluid is passing through these two pipes. I want to connect this pipe with this pipe, and we connect using a Bellow joints. Okay, we do not connect directly if the pipe length is very long. We do not connect directly those two pipes. We use a Bellow joint in between two pipes to accommodate thermal expansion or to accommodate some little deflection. Okay, so because of the pressure inside this tube, pressure inside this tube may, okay, excuse me. So pressure inside this tube may make this pipe, okay, so deflect, right? So to accommodate a little bit deflection between these two pipes, okay, or torsion between these two pipes, or some expansion like this direction expansion. So thermal expansion, or because high pressure create expansion of the pipe, okay? So we use Bellow joint in between them, okay, like this one. So Bellow joints are like very thin shape made up of steel body or some alloy steel, okay, alloy steel. So like this one, very thin structure. So that's why it can deflect, okay, based on the pressure inside the tube, and accommodate the movement of these pipes, okay? So very thin body. So to model these very thin bodies, we use a shell element. I will explain what is the shell element, and so we work with shell element in the ANSYS, okay? So tomorrow I will explain, but before analyzing that one, we have to create a model, right? So these are the dimensions of that model. So 20 millimeter, and what I'm going to create is, I just consider a line here, okay, and a line. So only outer layer I just consider, okay. So make this sketch like this one. So how many joints are there total? 10 joints. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So 10 joints. So total. So first I just only make one joint, and later I copy. So these joints 10 times. Okay. So 10 times using, you can use translate. Okay. Translate in CATIA. So you can either use ANSYS or ANSYS design modeler, or you can use CATIA. So yeah, I am assuming that this one is XY plane. In XY plane, you can also consider this one in YZ plane, okay, YZ plane. So it's a three-dimensional body, okay. So but if it is two-dimensional plane stress analysis, we have to make models in XY plane only, okay, in ANSYS or in CATIA. But three-dimensional body we can make, okay, this body, this sketch in a YZ plane or any plane, because it's a 3D surface body, okay, not 2D surface body. So three-dimensional surface body. So let's start shape design, generative shape design. Okay, why I am using generative shape here? Because I have to create a surface body, or you can also use mechanical design, wireframe and surface design. Okay, either you can use this one or you can use generative shape design. Okay, and name that one as Bellow joint. Okay, name that one as a Bellow joint. Okay, so consider XY plane. Make sketch in XY plane, and so as I said, I have to make this shape. Okay, so make this shape, and I make only up to here only. Okay, up to here, and later I copy the remaining things. Okay, so make that shape. So I'm going to use profile tool. So profile tool, so I can start from somewhere else here. Okay, because the length from the axis to here is 315 millimeter, right? 315 millimeter. So I can start from somewhere else here and draw a line, straight line. So later draw an arc, okay? Arc like this one. So when you drag your mouse towards right side, you can create arc like this one, okay? Concave arc. And draw line again, and again drag your mouse to create arc, okay, towards right. Okay, so like this one, because it's a half circle, okay, half circle. And again line up to here, and again drag your mouse. Oh, I missed with the drag. Okay, go to this point and drag your mouse. Yeah, like this one. Or you can consider circles or arcs, okay, just lines and all, you know, right, Kittia, very well. So I'm just directly making profile toolbar, making use of profile toolbar, okay. So cancel. After this one, escape. I don't want any line, okay, just up to here, up to here. And here, here tangency constraint is coming, that's okay, because this line and this arc is tangent to each other, okay. Wait, yeah, like this one. So many calls coming. So like this one, tangent to each other. And now give the dimensions from here to here. How much? 315? 315. And so I'm using KTR because you are familiar with KTR, right? ANSYS, you are not familiar. So you can use ANSYS design modeler also. And radius 7 millimeter, all radius 7 millimeter. So 7 is very small. And this is also 7 millimeter. And this is also 7. Oh, something happened. I have two monitors here. And this is also 7 millimeter. Okay, and why it is white? Okay, from here to here, 28 millimeter. Okay, it's given this problem. 28. So from here to here, 28. Okay. So making design using KTA or ANSYS takes time. I mean, analysis takes very simple because just we are apply internal pressure and fixed support, okay, and solve, right, and check the solution is accurate or not. So, but making the design. I mean, using a ANSYS or CATIA takes time. And now I copy. So because I finish right here. So remaining Bellow joints are also same. I copy this one here, like this one, okay? Like this one. How many times? 9 times. Remaining 9. The total 10 joints are there, remaining 9. Okay, yeah. This one, and this one, this one, and this one. Select and use translate. Okay, where is translate here? Mirror. You know, right? Mirror. Symmetry here. Translate. Okay. So translate 9 times. And the starting point, you can select this point or this point or this point, any point. Okay. So set starting point is this one. Okay. Start point. And move that point, translate that point to here, right here. Another point is here. Okay. Okay, and I finished. And if after again we have to make one more line here. So there is one more line at the end. Okay, yeah. So yeah, one more line. So right now our figure is like this. Okay, our figure is like this one. So make one more line here and erase the remaining arc. Okay, and erase the remaining arc. So how to make line? So just line. Use line. So start from here. Okay, you can start from here. Center of the arc. This is a tangent. So don't. You can do the tangency constraint later also if you don't see that. And 20 millimeter. And erase the remaining arc. Okay. So now I created surface. I mean, sketch for surface body. Okay, just this is white color because when I translate, some of the constraints are not coming. Okay, you have to make here everywhere tangency, but it's okay. So it's okay. Here when we use translate, right, I just keep all the boxes. Duplicate mode means keep the original one also, like that one. And okay, and here horizontal is not. So let makes all constraint work here to keep constraint. That is better. Okay, even it is not constrained, no problem. But to get more accurate solution, make sure that there are no errors. Okay, right now there is no error, but there may be some little error. Horizontal constraint and tangency constraint. It's not coming. I did not select tangency. Why? So this arc and this line, tangency. Yeah, we have to do all these things like that, tangency, but that's okay. So now go outside. After that, what we have to do? Revolve, right? Revolve. Like shaft in part design. Okay. So this is our sketch. Okay. Revolve this sketch about the vertical axis. So this one is vertical axis. Vertical axis is nothing but y-axis. Okay. So revolve that one 360 degrees. Okay. So where is the revolve tool here? Next tool, revolve. Okay. Revolve and 360 degrees. And revolution axis is vertical axis. Okay. So this one is surface body. So 3-dimensional surface body. Okay. You can hide the sketch. Okay. Hide. So we have to save this one. To read this one in ANSYS file, save as. So Bellow joints. So Yeah, you can save anywhere. Bellow joints CATIA part is CATIA part or CATIA part. So I mean, in future you want to modify using CATIA, you can save in CATIA part. Save that one, and also we have to save that one to read in ANSYS. We have to save in HTTP format, okay, or IGS format. IGS format or HTTP format, okay. So like this one. So I use HTTP. So Bellow joint HTTP, okay. This is a must. Otherwise, we cannot read that one in ANSYS. So save. So that is the end of this video. So later in next video, I will show you how to make this one using CATIA. Okay. So tomorrow we're going to work with this one also. Yeah, dear students, after creating the geometry file model, we have to simulate this one. This one is Bellow joint subjected to internal pressure 0.5 megapascals. So there is a pressure of gas acting on Bellow joints, and you know, right, where we use Bellow joints to connect between two pipes. So to accommodate some deformation between two pipes. Okay, here one pipe and here another pipe. So here we connect this one to pipes. So this here and here fixed support. Okay. And what else we have to give inside? Pressure acting 0.5 megapascals. Only those conditions we have to give. And we have to find the hoop stress. Okay, here. So we know, right, normal stress we has X and Y and Z. So sigma X, sigma Y, and sigma Z. Okay, that is a normal stress. But hoop stress is circumferential stress. I want to find the stress in circumferential direction, okay, like this one, in this direction, okay. So circumferentially like this. So that is the hoop stress, okay, circumferential direction. So here we have to change the coordinate system here, okay. So Cartesian coordinate system, if you give just sigma X or sigma Y and sigma Z, sigma X means axial stress, okay. So not hoop stress. We have to change the coordinates. So let's start ANSYS bench. And the static structural. So change the material properties, okay. Stainless steel, this one is SU316, means stainless steel, 180 GPa, and in smallness is 180 GPa, and Poisson's ratio 0.28. Okay, change those values correspondingly. So Young smallness is 180 GPa, right? So here 200 instead of 200, 180. Or 1.811 you can type, okay. And Poisson's ratio is 0.28, 0.28. So only those things we have to change. You can change the material name, no problem. Just it's okay. Close this one. And geometry, I already created a model, right? So import that geometry, Bellow joints, surface. Okay, Bellow joints, surface model. You can download this model from your Google Classroom. Okay. Yeah, and let's check how it is imported. So generate. So you can give the thickness here also. Bellow joint surface body thickness is 0. Okay, cannot give here 0.8 millimeter. Okay, here this is given 0.8 millimeter thickness. Okay. So we model that one with shell elements. Okay, shell. You can also model with one 3D elements like tetrahedron elements if we use 0.8 thick surface. Okay. So I also provided the 3D file. Okay, surface file and 3D model file, surface model file and 3D model file. I provided both the files. Okay, you can work there. 0.8 millimeter. Okay, below joint 0.8 millimeter thickness, material properties I have given, and the mesh. So here 19.281 mesh size. So the problem with this mesh size is 19.281. It's giving very fine mesh. So with the free license, we cannot solve this problem. Okay, free license not giving answer for this one, because with the free license we can solve only for limited number of nodes. Okay, so increase the mesh size to let's say 500 mm. 500 mm. I don't know whether it work or not. 500 mm, but you will get very less accurate solution. But so if you have a genuine ANSYS license, you can reduce further. Okay, to get accurate solution. And static structure, what we have to give fixed support. Okay, fixed support here, this inside this, sorry, this one and this one, right? And also because we are connecting this one to rigid pipes, that's why it's a fixed support. Okay, yes, this one is fixed support, two sides, insert fixed support. And also select all the things, all bodies. So you can select this one and select all. Okay, right click there and select all. So including fixed support also you can select, that doesn't matter, or you can eliminate that fixed support, no problem. Insert pressure and normal to that surface, right? So 0.5 megapascals, 0.5 MPa. Okay, make sure that you are in millimeter units. I am in millimeter unit. Okay, if you are meter unit, 0.5 E6 you have to give. So this fixed support. So what we have to find? We have to find the total deformation, and also we have to find the hoop stress. So for that we have to change the coordinate system. Okay, because we have only, when we use normal stress, right, we can only find sigma x, sigma y, and sigma z in this direction. But I have to find the stress in circumferential direction. So we have to work in cylindrical coordinate system. Okay, right now we are in Cartesian coordinate system, global coordinate system. Change, insert coordinate system, rename that one to user cylindrical, any name. Okay, coordinate system. And yeah, so here not Cartesian, cylindrical, and geometry defined by global coordinate system. Origin is same as the cylindrical coordinate system. Okay. Origin is x, y, z, 0, 0 here, right? We have the same. So just select that one as global coordinate 0, 0. And principal axis is this one. Principal axis means axial direction. Yes, we have to change that one, right? So cylindrical coordinate system means radial coordinate, okay, and axial coordinate and circumferential, tangential coordinate, right? Like this one. So principal axis is z-axis, okay? Z-axis. So z-axis in the cylindrical coordinate system is y-axis, right? In Cartesian coordinate system. So axial axis, right? Z means axial direction is global y. Okay. So x is the radial direction in cylindrical coordinate system. X is radial direction, Z is axial direction, and y is circumferential direction. Okay. So we have to change here. Principal axis is z-axis. That means this one, axial direction. Okay. And that is defined by global y coordinate, right? This is global y coordinate. Okay. So that is the thing here. We have to modify like this. Okay. So because we have to find the stress in this direction, right? Stress in this direction. So that is cylindrical coordinates we define, right? Y direction is that is the circumferential direction, hoop stress we have to find. And what we have to find? We have to find the deformation, total deformation or directional deformation. Directional, okay, I already added. So directional, we can change that. Rename that one to circumferential deformation. And that is defined by directional deformation. So what is the coordinate system? Cylindrical coordinate system and y-axis. Circumferential direction is y-axis, right? Okay, and also normal stress. Normal stress, the same. Which direction? Y-axis of cylindrical coordinate system. Okay, y-axis of cylindrical coordinate system, that is normal stress. We have to find the hoop stress, okay, or you can rename that one as circumferential stress or hoop stress. Okay, when we design some vessels subjected to pressure, we design for axial stress as well as hoop stress, circumferential stress. Okay, so circumferential stress is main thing when something is subjected to pressure vessels. But I don't think we can solve this problem because the mesh size is now 500 millimeter, right? I think this one is very complicated structure, many number of nodes it create. So I don't know whether we can get the solution using free version of license, okay, academic version. So it take very long time for meshing. Because this one is very complicated structure, right? So it consists of many intricate parts. Yeah, meshing finished. Okay, yeah, we are getting solution. That's good. 500. I used 500 millimeter mesh size. Okay, you can check. Reduce the mesh size further and check the result. Okay, so total deformation is 0.28. Okay, so we can change it. So when this pressure vessel is subjected to like that one, the Bellow joint subjected to pressure, it deformed like that. And hoop stress is 148 megapascals. Hoop stress means in this direction. You can also find the axial stress, okay? Axial stress, insert stress, normal stress in the z direction or y direction of global coordinate system, okay? Or z direction of cylindrical coordinate system, both are same, okay? Y axis of global coordinate, z axis of cylindrical coordinate is axial direction. And also I want to solve for structural error because we are using very big mesh, right? Let's see what will be the structural error. Yeah, so this one is 241, very high. The structural error also very high. That means the accurate solution is not so accurate, okay? 0.47 is very high, right? When you zoom that one, okay? So you can reduce the structural error by modifying the mesh, okay? Consider triangular elements, okay? And reduce the mesh size, but you cannot reduce beyond some point that gives the very, I mean, we cannot solve if the mesh size is very, very large or mesh very, very fine, okay? Element size is very, very small, or mesh size means your number of nodes very high, then we cannot solve using free lattice. Okay? You can check that one. It's very high value. Okay, strain energy value is very high. So it's not accurate solution. Okay, so I don't know whether these results are correct or not. Okay, we have to increase the mesh size, reduce the mesh size, and solve again to get accurate solution. Okay, that is the end of Bellow joint simulation.